Welcome back to AI.Code.Cast. I always get excited when we get to dive into a classic coding problem.
Oh, yeah.
And today's topic is a real brain tickler,
Mm.
the maximum frequency stack.
Yes. It sounds straightforward at first, but trust me, it has some hidden depth that'll really make you think about how to use data structures effectively.
Exactly.
Yeah.
You sent this one in, and it looks like you're gearing up for a technical interview.
Right.
Yeah. So let's break this problem down and explore different approaches.
Sounds good.
So imagine we have a regular stack, right?
Mm-hmm.
We can push elements onto it and pop them off.
Right.
Last one in, first one out, the classic LIFO structure.
Right. But in this case, we have an added challenge.
Okay.
When we pop from the stack, we don't just want the last element added. We
Right.
want the most frequent element in the whole stack.
Okay, so let's say we have a stack and we push the numbers 5, 7, 5, 7, 4, and then 5 again.
Okay.
What happens when we pop?
The first pop would return 5, right? It's appeared 3 times, making it the most frequent element so far.
Makes sense. But what about the next pop?
Yeah.
There's a 5 and a 7 that both appear twice.
That's where the second part of the challenge comes in.
Okay.
If there's a tie in frequency, we need to prioritize the element that was added most recently.
Right.
So in this case, the second pop would return 7, even though it has the same frequency as the remaining 5.
Ooh, I see. So it's like a double-layered prioritization.
Exactly.
Frequency first and then recency if we have a tie.
Precisely. It's all about finding the perfect balance between how often an element appears and how recently it was added.
This is where it gets really interesting.
Yeah.
Now we need to figure out how to actually build this maximum frequency stack.
Right.
Where do we even start?
Let's start with a brainstorming session.
Okay.
What's the most obvious approach that comes to mind, even if it's not the most efficient?
Well, if we need to know the frequencies and the order elements were added, we could just sort the entire stack every time we want to pop. We'd figure out the frequencies, sort them from highest to lowest, and then within each frequency, we sort by recency.
That's a classic brute force approach.
Yeah.
It's definitely a way to get the right answer, but is it the best way?
Probably not.
Oh, no.
I mean, sorting a large stack every time we pop sounds pretty time-consuming.
Exactly. Think about the time complexity of sorting algorithms.
Yeah.
It's usually something like O(n), log n, where n is the number of elements.
Right.
If we do that for every single pop operation, it's going to be a performance nightmare, especially for large stacks.
Okay, so brute force is out.
Yeah.
We need a more elegant solution. I have a feeling this is where those clever data structures come into play.
Yeah.
Any hints you can give me?
Let's think about what we need to track.
Okay.
We need to know the frequency of each element, and we need a way to keep elements with the same frequency organized by recency.
Okay.
What data structures are good at those things?
Frequencies make me think of hash maps. They're like dictionaries where we can associate a key, in this case the element, with a value, its frequency.
You're on the right track. Hash maps are perfect for keeping track of frequencies.
Okay.
Now, how about maintaining order within each frequency level?
Okay.
What structure is designed for that?
Stacks. They're all about order last in, first out.
Uh-huh.
So maybe we could use stacks to store the elements within each frequency level.
Bingo. You're getting close to a really elegant solution.
Awesome.
Now, how can we combine hash maps and stacks to create our maximum frequency stack?
Okay. Let's see. What if we use one hash map to keep track of frequencies, just like I said?
Yeah.
Each time we push an element, we update its count in this hash map.
Perfect. Let's call that freak map for easy reference.
Okay.
So far, so good.
Then we could have another hash map where the keys are the frequencies and the values are stacks.
Right.
So each frequency level would have its own stack to keep track of the elements with that frequency.
Exactly. Let's call this hash map stack map. Now we're talking. But how do we know which stack to pop from?
That's where things get tricky.
Yeah.
We need a way to keep track of the maximum frequency we've seen so far, right? Otherwise, we'd have to search through all the frequency levels in StackMap.
You're absolutely right. We need to track that maximum frequency so we know where to go directly when it's time to pop.
So maybe we could have a separate variable. Let's call it maxFreq.
Okay.
That always stores the highest frequency we've encountered so far.
Yeah.
Each time we push an element, we check if its frequency is greater than our current maxFreq and update accordingly.
That's brilliant. Now we have a direct pointer to the stack that contains the most frequent elements.
Okay.
But what about those ties we talked about?
Right.
How do we handle situations where multiple elements have the same maximum frequency?
Well, that's where the beauty of stacks comes in, right? Since they're LIFO, the most recently added element will always be at the top of the stack.
Yeah.
So when we pop from the stack associated with maxFreq, we'll automatically get the most recent element among those with the maximum frequency.
You've got it. You've just described a really clever and efficient way to build a maximum frequency stack using hash maps and stacks.
Awesome.
It's a classic solution that showcases the power of choosing the right data structures for the job.
I'm starting to see how this all fits together.
Yeah.
We've got our freak map to track frequencies, our stack map to organize elements by frequency, and max freak to act as our guide.
Yeah.
But how does this actually work in practice? Can we walk through a few examples of pushing and popping?
Absolutely. Let's explore how these data structures work together to handle different scenarios. All right, let's imagine we're pushing the number 8 onto our maximum frequency stack for the first time.
Okay.
What do you think happens to our data structures?
Okay, let me think this through.
Yeah.
First, we'd head over to our freak map and check if 8 is already there.
Right?
Since it's brand new, we'd add it with a frequency of 1.
Exactly. Now, what about max freak?
Well, our current max freak is probably higher than 1 since we've already been adding other numbers.
Yeah.
So we wouldn't need to update it just yet.
Right on. Now, we need to get that 8 into the right spot in our stack map.
So we'd go to the frequency level 1 in stack map.
Yeah.
If there's already a stack there, we'd just push 8 onto it. If not, we'd create a new stack for frequency level 1 and put 8 in there as the first element.
You nailed it. Now, let's say we push another 8. What changes?
This time when we check freak map, we see that 8 is already there.
Uh-huh.
So we bump its frequency up to 2.
Good. And since 2 might now be our new highest frequency,
Right.
we'd check if it's greater than our current max freak and update max freak if needed.
Okay, I'm following along.
Yeah.
Then we'd go to the stack for frequency level 2 in stack map and push the new 8 onto that stack.
Exactly. Now, let's say we've been pushing a bunch of numbers and it's finally time to pop an element. How would you approach that?
All right, popping time.
Okay.
First, we check our handy max freak variable to see what the highest frequency is at the moment. Then we go to the stack in stack map that corresponds to that max freak.
And what happens next?
We pop the top element from that stack. That's the element we return as the result of the pop operation.
Okay.
Simple and elegant.
You've got it. But remember, whenever we pop an element, we need to make sure our frequency tracking stays accurate.
Right. So after popping, we go back to freak map and decrement the frequency count of the element we just removed.
Yeah.
This ensures that our frequency counts are always up to date.
Excellent. Now, what if after popping an element, the stack associated with max freak becomes empty?
That's an interesting edge case.
Oh.
It means there are no more elements with that particular frequency.
Exactly. So what should we do with our max freak tracker?
We need to update it to reflect the new highest frequency present in the stack.
Right.
So we decrement max freak by 1 and then continue as normal.
Spot on. By decrementing max freak, we ensure that the next time we pop, we're looking at the stack with the next highest frequency.
This whole system is so clever. It's amazing how these data structures work together in harmony to maintain frequencies, keep track of recency, and give us that constant time performance for pushing and popping. It's like a well-choreographed dance.
I agree. It's a very elegant solution, but, there's another approach that's equally fascinating, using a priority queue.
Ooh, a priority queue. That sounds intriguing. I've heard of those, but I'm not sure how they'd apply to this problem.
Well, a priority queue is a data structure that always keeps its elements sorted based on a certain priority.
Right.
In our case, we need to prioritize elements based on both frequency and recency, right?
Right, just like in our hash maps and stacks solution.
Yeah.
But how do we get a priority queue to juggle 2 different criteria like that?
That's where the cleverness comes in. We can represent each element in the priority queue as a tuple.
A tuple. I'm picturing those as little containers that can hold multiple pieces of information.
Exactly. Each tuple will contain the element itself, its frequency, and a timestamp indicating when it was added. This way, we can encapsulate all the information we need to prioritize correctly.
Okay, so we've got these tuples with element frequency and timestamp. How does the priority queue use this information to keep things sorted?
Here's the key insight. Most priority queue implementations use a min-heap structure.
Oh, yeah?
That means they're naturally good at finding the smallest element quickly.
So how do we leverage that for our maximum frequency stack where we want the highest frequency and most recent element?
We get a little sneaky with our tuple values.
Oh,
Instead of storing the frequency and timestamp directly, we store their negated values.
negated values. Wait, are we talking about turning them into negative numbers?
Exactly. It's a clever trick.
I see.
By using negative values, we effectively reverse the sorting order of the priority queue.
I see. So now the tuple with the most negative frequency and timestamp will actually represent the element with the highest frequency and the most recent addition. It's like turning the problem upside down.
You've got it. It's a bit counterintuitive, but it works beautifully with how priority queues are structured.
All right, I'm starting to see how this could work, but how do the actual push and pop operations play out with this priority queue setup?
Let's walk through it step by step.
Okay.
When we push a new element, we first check if we've seen this element before.
Okay.
We can use a hash map, just like in our previous solution, to keep track of frequencies.
So if the element is already in the hash map, we increment its frequency count. If not, we add it to the hash map with a frequency of 1.
Exactly. Then we create a new tuple for this element containing its value, its updated frequency, remember negated, and a new timestamp.
And we push this tuple onto our priority queue.
Mm-hmm.
Since we're using negative values, the priority queue will automatically place it in the correct order based on both frequency and recency.
Precisely. Now for the popping part.
Yeah.
What do you think happens when we need to remove an element?
With a priority queue, popping is super easy, right?
Mhm.
We just grab the top element, which, thanks to our clever tuple structure and negated values, will always be the element with the highest frequency and most recent timestamp.
You've got it.
Okay.
We extract the value from this tuple, return it as the result of the pop operation, and then just like before, we decrement the frequency count of that element in our hash map.
So we've popped the most frequent and recent element, all thanks to this ingenious priority queue setup. It sounds incredibly efficient, especially for popping.
It is. Both pushing and popping operations have a time complexity of O log n, where n is the number of elements in our priority queue.
Okay.
This is because heap operations, like inserting and removing elements, have logarithmic time complexity.
Ologen is pretty impressive.
But how does that compare to our previous solution with hash maps and stacks, which had constant time complexity for both pushing and popping?
You're right, the Hashmaps and Stack solution is theoretically a bit faster, but there's a trade-off here.
Right.
The priority queue solution might be a tiny bit slower in terms of time complexity.
But it's conceptually simpler in some ways.
I see what you mean.
Right.
We only need one data structure, the priority queue, whereas the other solution used 2 hash maps and multiple stacks.
Yeah.
It feels a bit more streamlined.
Exactly. It's all about choosing the right tool for the job. Sometimes a slightly less optimal solution in terms of pure performance might be preferable if it's easier to understand and maintain.
This has been a fascinating exploration of 2 very different approaches to the maximum frequency stack problem.
Yeah.
I'm amazed by how we can use these data structures to create such elegant and efficient algorithms. It really shows the power of understanding how these tools work and how to apply them creatively.
I agree. It's a testament to the power of understanding fundamental data structures and how they can be combined and manipulated to solve complex problems. And before we wrap up, let's take a step back and revisit that brute force approach we discussed earlier.
Yeah, the one where we sort the entire stack every time we pop.
Exactly.
Why revisit that? We already established that it's not very efficient.
You're right. It's not the most optimal solution in most cases, but I think it's worth revisiting for a couple of reasons.
Okay, I'm intrigued. What makes this brute force method worth another look?
Sometimes even a simple approach can be surprisingly effective, especially in certain scenarios.
Okay,
Plus, it's a good reminder that there's often more than one way to solve a problem.
fair enough.
Huh.
So how about we explore this brute force approach a bit further?
Let's do it. It might surprise you how useful it can be in the right context. All right, let's dust off this brute force approach and see if it has any hidden gems. Remind me again how it works.
It's all about sorting.
Yeah.
Each time we need to pop an element from our maximum frequency stack, we sort the entire stack. First, we sort by frequency, making sure the most frequent elements bubble up to the top.
Right, so far so good. But what about those pesky ties where multiple elements have the same frequency?
That's where the second level of sorting comes in. Within each frequency level, we sort again, but this time by recency. The most recently added element among those with the same frequency gets placed at the very top. So it's like manually recreating that layered structure we achieve with the hash maps and stacks. But instead of using hash maps to keep things organized, we're just sorting the whole stack every single time.
Precisely. Now, we already talked about why this approach isn't ideal in terms of efficiency.
Yeah, sorting algorithms generally have a time complexity of O(n) log n, where n is the number of elements.
Right.
Doing that for every single pop operation just doesn't sound scalable.
You're absolutely right in most scenarios, especially when you're dealing with large stacks and frequent pop operations. This brute force approach would be a performance bottleneck.
But you mentioned earlier that there are times when even a simple approach like this can be surprisingly effective.
Yeah.
I'm curious, when would this brute force method actually make sense?
There are a few niche scenarios where this approach might not be so bad. For example, imagine a situation where the stack is relatively small. Say less than 100 elements?
Okay, I can see how sorting a small stack wouldn't be as computationally expensive. It's like sorting a deck of cards versus sorting the whole library.
Exactly. And if you're not popping elements very often, maybe just a handful of times, the overall performance impact might be negligible.
So if we're in a situation with a small stack and infrequent pop operations, this brute force method could actually be a viable option.
It could be, especially if simplicity and readability are top priorities. Sometimes it's better to have a solution that's easy to understand and maintain, even if it's not the absolute fastest in terms of theoretical performance.
That's a great point. As much as we love optimizing for speed, sometimes over-engineering a solution can lead to complex code that's hard to debug or modify later on.
Exactly. It's all about finding that balance between performance and practicality.
This has been a fantastic deep dive into the maximum frequency stack problem. We've explored three distinct approaches: the elegant use of hash maps and stacks for that blazing fast constant time performance, the clever priority queue solution with its balance of speed and simplicity, and now a fresh perspective on the often dismissed brute force approach. It's amazing how each solution highlights different aspects of problem solving and the trade-offs involved.
It's been a great journey through the world of data structures and algorithms, wouldn't you say? We've seen how understanding the strengths and weaknesses of different tools allows us to craft solutions that are tailored to different needs. And sometimes, even revisiting a simple approach can reveal valuable insights.
Absolutely. So to our listeners out there, the next time you encounter a coding challenge like the maximum frequency stack, remember to consider all your options. Think about the constraints of the problem, the performance needs, and the complexity of the code itself.
And who knows, maybe you'll even come up with a completely new and innovative approach. There's always room for creativity and ingenuity in the world of coding.
On that note, thanks for joining us on this deep dive into the maximum frequency stack. We hope you've learned something new, sparked some ideas, and maybe even feel inspired to tackle some coding challenges of your own.
Don't forget to check out the show notes for some helpful resources, code examples, and maybe even a challenge or two to test your understanding.
Until next time, keep coding, keep exploring, and keep that passion for algorithms burning bright.